So I'll be talking about a very special class of neutron stars, that is one whose life we believe is dominated and shaped by the magnetic field. So before starting, let me actually start by asking the question, why is it that we believe that there are neutron stars whose life is actually dominated by the magnetic field? What I have here are, it's a very complete sample up to, this is basically 2003, of all neutron stars for which we have X-ray measurements, so we reasonable distance estimates, for which we can therefore measure the X-ray luminosity and also as well as the age. What you see as far as curves here, these are standard cooling curves for a range of masses and for different types of envelope compositions. This is B equals 0, but as far as cooling models are concerned, B equals 0 is equivalent to B equals 10 to the 12. So typical magnetized neutron stars with magnetic fields of 10 to the 12, as we're used to know, it won't make much differences in terms of these cooling curves. So something that is quite apparent, quite striking by these figures alone, is that there are a number of objects up here, there are the ones in red, for which no matter how much you play with varying masses, varying everything you can think of about a neutron star, just the luminosities are way too high. We cannot account for them with any of these cooling models. So this is reason number one. Something that I should also mention, that for these classes, for these objects, they are very slow. Their extra luminosity are much larger than the rotational energy loss. In principle, you can imagine that a fraction of the rotational energy could be converted in X-ray radiation. That's something that we know to happen for young pulsars, but this is not the case for these objects. They're also isolated, no companion, that can save your life by accreting onto you and giving you, therefore, producing extra luminosity by accretions. Historically, they have been classified as anomalous X-ray pulsars and soft gamma ray repeaters. The anomalous word here comes from these very high luminosities, and soft gamma ray repeaters have also some extra properties which will become apparent in the next slide. So these same objects which have these very high luminosities, unaccounted for, also display a variety of other quite interesting phenomena. Both the AXPs, short for anomalous X-ray pulsars, and the SGRs, the soft gamma repeaters, display occasional bursts of radiation seen in hard X-rays. These are in two different types. There is one type which is short duration, so sub-second, peak luminosity up to 10 to the 41 arc per second. And frequency can vary from object to object, but it's roughly between weeks to years, seen in both XPs and SGRs. On top of this, the SGRs also display some occasional, very rare, like over time scales of tens of years, very giant flares of radiation seen mostly in gamma rays. Now, what you see here, that the durations are much longer, hundreds of seconds, and the peak luminosity can be on the order 10 to the 44, 10 to the 45 erg. If you combine luminosities with duration, you see up to 10 to the 46, even 10 to the 47 ergs can be released by these stars in one event alone. So the big question, and I put past because by now we think we understand that, has been for a couple last decades, so 90s and early 2000, the big question was, what is the energy source for both this enhanced X-ray luminosity as well as the outbursts that we see in these objects? We believe that it is magnetic energy, the culprit, and I will discuss what are the arguments for which we believe that magnetic energy can serve us to explain the phenomenology that we see. First of all, just the order of magnitude estimates. There is enough energy to power the outburst. If you assume that you have a star which, instead of having your standard 10 to 12, 10 to 13 Gauss, as we know and love, has a, like, say, 2 orders of magnitude, a larger magnetic field, then there is enough energy, magnetic energy within the star, like a few times 10 to the 48 ergs, out of which you can therefore extract the 10 to 46, even 10 to the 47 ergs that you need at once to power an outburst. So at least energetically, we have it there. And over over a number of years, papers by Chris Thompson and Robert Duncan have showed how you can go from a lot of energy within the star to this outburst. The basic idea is that occasionally the stresses are strong enough that will break the crust, and that will trigger a series of events that leads to an outburst, which can be gamma rays or X-rays if the breaking is on a much smaller scale. So, okay, so there was one as far as the, at least the outburst goes. Now, what about the X-ray luminosities? These are some early calculations. There have been many, many more, but just to give the idea. If there is a magnetic field in the star, then the temperature that you infer as the function of the neutron star age can be much larger. Therefore, much stronger temperature implies much stronger, much larger X-ray luminosity for the same surface area. This is, again, an example with, so B equals 0 is, think of 10 to the 12 as a typical neutron star, and then it goes higher with the stronger magnetic fields. So strong B fields can also account for this enhanced X-ray luminosities. And then last, to complete this puzzle, if we plot the PP dot diagram, this is a diagram of period versus P dot versus period, in which if the star is slowing down only by dipole radiations, then lines of, so lines in this direction represent the age, and lines in this direction provide a measure of the dipolar component of the magnetic fields. If you take these objects for which P and P dot has been measured, you place them on the PP dot diagram, you see that actually they do occupy a region which is in the very high magnetic field range. So it all fits together in this picture that we're actually seeing objects with extremely high magnetic fields. Now, to put in perspective, just to give you a sense of how strong is strong, this is the magnetic field compared to a number of other magnetic fields strengths that can be maybe more familiar to you. As you see, magnetars are by far the strongest fields that we know of in the universe. It's really where nature goes at its extreme. So this is where we are. Okay, so with that introduction, the question is, where are we now with research in magnetars? What are the current questions that we're trying to answer? So the magnetar theory, as developed by Thomson Duncan over the years, has set the ground for understanding single outburst events and why they happen. However, observations have provided us with a lot of puzzles that we're now in the process of trying to understand. So first of all, I said that there are, these magnetars manifest themselves as AXP, these anomalous X-ray pulsars, which have more moderate activities. They don't appear to show large flares. And also that there are certain properties related to where the outbursts are distributed with respect to the phase of the pulsation. So for example, in the XPs, the outbursts tend to be correlated with the maximum of the pulse profile, so in the region where the object is hotter. On the other hand, if you take this other class of objects, they generally are more active. They display large flares by definition. That's how they've been named for the discovery. And also the outbursts, the smaller ones, tend to occur, they're uncorrelated with phase, meaning that they will occur all over the surface of the neutron star. So these are differences that for which the standard theory of magnetar does not give any immediate answer. Moreover, life has become much more interesting, so to speak, in the last couple of years. So this has been really recent updates as what has happened in terms of observations and therefore the theory that's followed. And this is summarized in this, again, it's a PP dot diagram. It's just the upper part, and it's more updated with respect to the one I showed you before. Because what I wanted to show is what happened more recently. That is, so let's look here. We have this star here that represents the standard magnetars. And then there are these objects here, which they're called high radio pulsars. So these are new pulsars that have been discovered, which which have a magnetic field, as you see here, that would make them as magnetars. However, they behave as regular pulsars. They're very quiet, relatively quiet. As, they don't give this giant outburst. They have low luminosities, they're low X-ray luminosities, just any regular radio pulsar, but it's in a magnetar region. And then on the other side of the same puzzle, there have been some neutron stars which have been discovered as being soft gamma repeaters. This one in particular was the first one discovered in 2010, okay, which was in a region where you would not expect a magnetar. And there have been, like for example, you can take two objects here, one which is a pulsar, another which is very close in magnetic fields, and they have very different behaviors. This has been very puzzling and has given rise to some of the more current questions that as theorists we're trying to address, and it is, if the magnetic field is the main driver, what is that makes this variety phenomenology that we observe? I just have a couple more slides. So this is something which we're trying to start working in this direction, so trying to have a unified picture which can allow us to understand from first principle what is that determines this behavior that we see. To this purpose, we have coupled magnetothermal evolution models that Jose Pons and collaborators have developed over the year with computations of the magnetic stresses on the neutron star in order to see how often these stresses happen, where they happen, and how they vary with the age and different components of the magnetic field of a neutron star. In fact, something I should say that while what we measure is only the dipolar field from pp dot, as a theorist, you can also model what you don't see, what you don't measure directly, and it is the toroidal component. And that, as we'll see, plays a very important role. So I'll show two quick movies of this simulation where this is the, I went back, sorry. What you see here, it's the age of the neutron star in the top, and the color when it becomes light blue, yellow is where a stress occurs on neutron star, on the neutron star. And then I show a second one, which is a higher B field, and you see how there are many more stresses occurring on the neutron star as it ages. But as it ages, the number of outbursts declines with time. Okay, so the summary is that basically so just summarize the result of simulations. So what we find by with this simulating the life of a star is that there is basically no fundamental difference between what makes an XP and SGRs. For the same magnetic field, the younger objects are more active, like people. Their outbursts are more energetic. At the same age, stronger B, more frequent the outbursts. Younger objects tend to be more SGR-like, what we observationally define SGR. Older object more like XP-like, but practically there's not really a physical difference between the two. And in fact, observation is starting to blur the line. And also, this is just the last one. And then there is summary. Sorry for going 1 minute over time. Also, the rate of B field is as expected depending on both dipolar and toroidal components. Therefore, neutron stars with the same dipolar field, which is what we measure, can have very different X-ray luminosities and very different outburst rate. So practically, this apparent puzzle that we have been seeing, two neutron stars appear in the same location on the PP dot diagram that behave very differently. If you account for the fact that they can have very strong toroidal component, then you can explain these differences. One star had a much stronger toroidal component, which we don't measure directly than the other, and then one can appear as a magnetar as we would define it, and the other would appear more as a regular pulsar. So the summary is that we are beginning to unravel this puzzle of what creates neutron star behavior with the strong fields. Detailed results on outburst rates and all these things are dependent on details on neutron star interior crust and atmosphere. So once we put together all the data from X-ray spectra, which gives information on the temperature, timing, which gives information on pulse profile, giving information on the temperature distribution, and then outburst rates will hopefully make big strides towards understanding more of the neutron star interior and how it's modified by strong B fields.
Connecting to Andrew Steiner's talk
Right.
at the start, can you see any practical way of limiting how large the field could be inside any pulsar, not just a magnetar, being 30 or 100 times larger than what you measure on the surface? And is there any possibility that it could be so large that it would make a qualitative difference to the equation of state and change the mass-radius relation and so on?
Right, so magnetic fields above 10 to the 16, 10 to the 17 Gauss are believed not really be sustainable for a neutron star. In terms of trying to figure out what the magnetic field for us to be able to tell what the magnetic field in the interior is, so this toroidal field, which is mostly confined in the crust, so there are ways in which observation can help to detect, so to speak, this field which we don't measure by PP dot. This is something in which actually we've just been working. So a very strong B field, the toroidal field, breaks the symmetry with respect to the theta symmetry with respect to neutron star. So theta from pole, so the theta variable. So what happens is that in the pulse profile, for example, if you have a dipolar field alone, or a dipolar field which is an external field dominating, you see a double X-ray pulse profile. If you have an internal field which is highly dominating, so a strong, very strong toroidal field, what happens is that it will break the symmetry and tend to produce more single pulse profiles. So there are ways that we can see that observationally, relating theory to observation that way.